In the last class we had talked about how to add sound at different frequencies, and we had got this very important relation that it is in the mean square sense that the addition is valid. That is, if you have two sound sources, one emanating an acoustic pressure of P1, the other emanating an acoustic pressure of P2, it is the mean square associated with P1 and the mean square associated with P2 that gets added up to give the mean square of the total combination. That was true for different frequencies because omega 1 and omega 2 were chosen to be different. Now, let us just turn back once and see what happens if we choose omega 1 and omega 2 to be same. So, this time we are adding sound of from two different sources which are emanating at the same frequency. So, here you can expect that the above formula will not hold, and the reason for that can be understood from this derivation itself. So, this was the derivation that we did in the last lecture for the case of omega 1 and omega 2 being different. Here you will see that this term lives to see the light of the day. This term, which is omega 1 minus omega 2, will now give us 0, right. So, this underlying term is no longer going to be of the form which has 0 mean, because there will be a cos beta 1 minus beta 2 which remains, which is dependent upon the phase difference between the two sound sources, is going to be just a constant, right. But all other parts of the derivation is going to be identically same. You will get this term associated with the average value of this quantity. This quantity is again not going to contribute to the average value, this quantity is not going to contribute to the average value. So, you will have P1 square by 2 and P2 square by 2 as usual. Just in this term where both of these trigonometric terms were shown to have a 0 average effect, that is not going to be true, only the second term is going to have a 0 average effect, but this first term wherein you have omega 1 minus omega 2, that will be having an average effect associated with P1 P2 cos beta 1 minus beta 2, which is the cosine of the phase difference between the two signals multiplied by the product of the two. So, that part is clear. So, therefore, what you will get is something like this. So, here as we see that the mean square addition is not exactly valid, because together with the sum of the mean squares you get another term which is just dependent on the cosine of the phase difference between these two sources. So, we will keep this note and we will say that the phase difference of the two sources will definitely affect the RMS value of the total sound. So, that is when you have two sources which are emitting sound at the same frequency, and even from the concept of phasor, this fact that there is the issue of phase difference between the sources does affect, can be understood in a slightly different perspective. Maybe I will do that. So, if you look back at the phasor concept, let us say there are associated with each source we are giving a phasor representation. So, two sources, I will draw two phasors which are having a phase difference of beta 1 minus beta 2. Both of them are going to rotate at the angular frequency. The addition of these two is just going to be a vector addition of the two phasors which is going to rotate. So, as you know, the vector addition of the two vectors depend upon the angle subtended by the two vectors. So, therefore, the resultant phasor will depend upon the cosine of the phase difference. So, therefore, the mean square addition from would sort of fail. I would not say fail, rather it will sort of is limited, I would say, to the case of only where the frequencies are different. If the frequencies are same, then the mean square addition should include a phase factor related contribution. But then at times we tend to ignore this phase factor related contribution, but the reason for ignoring this phase factor related contribution has to be completely justified. We can ignore this phase factor related contribution if we are making a further assumption that the sound field is diffused. What does that mean? What happens in an enclosure problem such as this room or any other similar rooms, you as we understand, associated with the boundaries of your acoustic domain, you will get reflection. And since you already have 6 boundaries and in a cubical room of this sort, you will get multiple reflections, and each reflected wave will in turn produce further reflection, something like this. To illustrate, if you have I can only draw a 2D plot here. So, if you have an enclosure of this sort, if there is an incident wave, it will get reflected, and this reflected wave will further get reflected, and this reflected wave will further get reflected. So, each reflection in turn will induce additional reflections, and in totality it is a standing wave, that we understand, but this standing wave is actually a resultant of multiple reflections. That is what we have seen even in the case of 1D acoustics, which is nice and simple in terms of its analytics, but extrapolating those observations, we can understand that any 3-dimensional cavity will induce multiple such reflections. And further, another complication associated with these reflections is the fact that at times, or realistically speaking, these boundaries are not particularly planar. Maybe it does not affect so much significantly, but at times these irregularities in the boundary can cause further issues and further complications definitely with regards to a computational process. But once there is a multiple reflection associated with each reflection, you can understand that there will be a phase change, and therefore, the phase at any point, rather it is the phase difference beta 1 minus beta 2, that factor could be anything between 0 to 2 pi, because just like as I showed in the schematic drawing, there are multiple reflections, and these reflections can happen in a very it is very difficult in order to predict these reflections, so as to say, and therefore, the associated phase changes induced by these reflections are almost like a random quantity between 0 to 2 pi. So, therefore, we say that the cos of this random quantity which fluctuates between 0 to 2 pi can be anywhere between -1 to +1, but the expected value of it will be between these two ends, the mean value, so as to say, is going to be 0. So, the phase difference between the acoustic pressure generated due to two sources of the same frequency under this diffuse sound field assumption is therefore going to be random between 0 to 2 pi. And once you invoke this assumption, then you can say that the expected value, expectation in the sense of the theory of random variables, of this factor, which is the factor which was sort of playing a spoil sport for the mean square addition law, that factor can now be killed to 0. So, it is only under a diffuse sound field assumption that this phase factor can be killed to 0, and thereby we get back, even for the case of sources emitting acoustic waves at the same frequency, that the mean square addition will still hold, because this phase factor is now getting killed because of this diffuse sound field assumption. So, the moral of the story is thus, that if you have sources emitting different frequencies, go ahead with your mean square addition law. If the two sources are there or multiple sources are there, and so happens that the phase factor, the mean square addition will not hold in its totality, rather there will be an additional term associated with the phase difference between these two sources. So, that is the idealistic viewpoint, but then if you in cases of mostly cavity acoustics and interior acoustics, wherein there are multiple reflections expected and each reflection will bring about its phase difference. So, as a result, you can expect that the expected value associated with this phase factor quantity would be nullified to 0. In such cases, again the mean square addition will hold even for the same frequency case. The reason why I am iterating this is because of the next formula, which is pretty well known by the field engineers in acoustics and NVH groups, but probably it is not very well appreciated under what conditions this Db addition formula holds. So, let us take a look at the Db addition formula. It is a very handy formula for the noise control engineer in the field. So, as we understand that acoustics is linear, which means that the sound pressure created due to one source and the sound pressure created due to the other source can always be added up. But then we realize that it is not possibly worth talking in terms of sound pressure in pascals. We shifted our units from that of Pascals to that of a decibel scale, which is a logarithmic scale. And just to recall, the formula for sound pressure level SPL, or abbreviated as LP, is L underscore P, that is L subscript P I should say. That LP term is given by 10 logarithmic with the base 10, the RMS square of the pressure divided by P, the reference RMS value, which is taken as 20 micropascal and square of it. So, this is the sound pressure level formula that we had seen even in the last class. So, we could turn this round and look at it in this form, that P RMS square by P reference square is going to be 10 to the power LP by 10. So, LP by 10 and 10 to the power of that is going to give this bracketed quantity. So, P RMS square is we know how to calculate the mean square of the pressure by now. That formula is also discussed. We discussed this with particular reference to both sounds at different frequency as well as sound at the same frequency. So, in either way you know how to calculate P RMS square. So, that part is clear. Now, the question is, if you have multiple sources, what we have seen, and let us say multiple sources emanating sound at different frequencies, then we understand that the mean square of the total sound pressure is going to be the addition of the mean square of the sound pressures emitted by individual sources. So, if you have n such sources, each of them emanating P1, P2, P3 and Pn, then in totality the mean square of the total sound pressure is going to be the sum of the mean squares of the constituent the acoustic pressure mean square of the acoustic pressures emitted by each of those individual constituents. So, this is just the mean square addition formula that we have derived in the previous class. If you wish to look back at it, this is the mean square addition formula that we had derived. So, we are applying that, we are appealing to that formula and thereby making this step ahead. And then we just simplify it in this form, which is nice and fine. And now we take 10, we refer to this part of the formula where we realize that the ratio of the mean square with reference to the reference square is going to be 10 to the power LP by 10. So, 10 to the power LP by 10 is going to be 10 to the power LP1 by 10, which is P1 RMS square by P ref square and so on. So, therefore, this is the addition formula in terms of LP. You could make it look better by taking a log on both the sides and multiplying with 10 again. So, that would mean that the decibel addition formula or the decibel level of the total sound which is created is going to be 10 log 10 of this quantity on the right hand side, which is appearing in the bracket, right. This is not an arithmetic addition, this is the formula for logarithmic addition. So, herein we must understand that if you have sound from one source to be let us say 80 dB and the other source to be let us say 82 dB, then it does not add up following the arithmetic law of addition, that is 80 plus 82 does not give you 162, rather it gives you as per this formula, right. So, this is the dB addition formula, and a very special case of this which is sort of very counterintuitive at first go is this. Let us consider that there are just two sources and each of them are sort of equal in their decibel levels, in the sound pressure levels that is being emitted. So, if each of them are emitting the same sound pressure level and there are just two of these sources, we can easily reduce this formula as LP1 equals to LP2, and since both of these quantities are going to be same, we might as well write it as 2 into 10 to the power LP1 by 10. And using the fact that logarithm of a product is sum of the logarithms. So, therefore, we take this as 10 times log of 2 base 10 plus 10 times log base 10 of 10 to the power LP1 by 10. So, that second term is not log of 10 to the power LP by 10 is LP by 10, and you have a multiplicating factor sitting of 10 here. So, therefore, this part is LP1 and log of 2 is roughly 0.340 or something like that. So, 0.3 multiplied by 10 is going to be roughly 3. There are some additional decibel points here, which is why this is an approximation. So, roughly what it means that if you have two sound sources which are emitting the same sound pressure level, then the total sound pressure level is not the arithmetic addition, but just 3 dB over and above the individual levels, right. So, this is obviously in these days we can easily code this up into a nice decibel calculator, and you can do that as a part of your assignments for sure. This is nothing, this is not a very big complicated program by any sense. You can have dB calculators, but at least in classically when computers were not so very well available. So, this was represented in a chart, the dB addition kind of a formula, and the way it is this dB addition formula comes in handy is in the following fashion. Let us say I am the manufacturer of this machine. I quote that this machine is going to emanate a sound of let us say L2 dB, right, but then this machine emanates sound of L2 dB under a perfectly quiet conditions when there are no other sounds there, right. In a standalone fashion, this the machine manufacturer quotes that this machine is supposed to emanate a certain decibel level, but then when this machine is planted into the factory, then this machine is there together with several other machines which produce sound. Some of them may be the same machine also, right. So, the question that the factory installation people would like to know and the safety inspector of the factory would like to know is that if this additional machine now comes and sits into the bay of the factory, then what is the new sound pressure level that is expected and what is the sound pressure level which the factory workers will be exposed to. So, the quick calculation for this is that first we measure the background noise. The background noise means what is the sound pressure level in absence of this machine, right. So, that comes out as let us say L1 dB, and we will probably in the next class look at how to do sound measurements also. There is instruments such as sound level meter which can quickly give us this sound pressure level in decibels. So, let us say that measurement can be done and that is L1 dB, and then the machine noise is L2 dB. So, therefore, the total noise is L1 addition, but this addition is a strange addition, it is logarithmic addition, it is not the usual arithmetic addition, and to stress this fact I have used a different symbol for addition, this plus sign coming within a circle. So, this is just my notation for a logarithmic addition as opposed to arithmetic addition. So, L1 logarithmic addition of L2 is the total noise that is expected, and that can be easily determined through this kind of a formula, or maybe in the shop floor where things have to be done fast and sometimes without a computer also. We have this kind of charts which really tells us that if the arithmetic difference of L2 and L1 is known, this is L2 and this is L1, this L2 minus L1 is simple arithmetic difference the way we have learnt it in our kindergarten. So, we do not need to worry about it. So, whatever is the difference, with that we need to add this value for it. For example, if the difference is 3 dB, then we need to arithmetically add 1.7 dB, right, and that will give us the total noise. So, this sort of a chart is very useful to convert this logarithmic addition formula to a very useful handy formula. And you will also note that if L2 and L1 are just identical, which means that L2 minus L1 the arithmetic subtraction is 0, then you need to add 3 dB to the component which is at the higher level. So, you have to, the formula goes this way, that L1 logarithmic addition of L1 and L2 is max of L1 L2 plus 3, and that is the maximum thing that you will get. The actual value has to be quoted from this sort of a graph. The actual value of L1 plus L2 will be max of L1 and L2 plus the value which you will read off from this graph, right. So, and also please note that this graph has a very sharp decaying characteristic. So, if L1 minus L2 is less than 10, So, you can see that there is hardly any addition that you need to make. So, at the level of 10 possibly you need to make a 0.5 addition, but at the level of 15 there is hardly any addition that you need to make. So, which means that if there are two sound sources and the sound pressure level between these two sound sources differs arithmetically by 10 dB or more, then you are not exactly going to contribute anything to the much to the total sound, right. Another way in which this formula should be very handy towards for practicing engineer is this. Suppose you are going to in a certain vehicle or in a certain component, you are going to add one extra component to that machine, and you are worried whether the addition of that component is going to affect the overall sound pressure level of this entire machine. Let us say, for as an example, you have a vehicle, and let us say the vehicle initially was without the AC or without the HVAC system. Now, you wish to add this HVAC system to this vehicle. So, the question is, by addition of this HVAC system, will the interior noise increase? If it increases, how much? And preferably it should not increase. Most of the times some of these or some ancillary units, let us say you want to change the fuel pump of an engine assembly, right. So, the engine obviously makes noise in itself, but the fuel pump in addition will make noise, and in totality it will contribute to the total noise emanated by the engine. So, as an engine manufacturer, I would like to choose a fuel pump for this engine which possibly is already at the level of 10 dB or lower. If I am sure that the fuel pump in isolation without the engine, just as a pump, if it is working, it is making noise which is less than 10 dB, then I am quite sure that when this fuel pump works together with my engine, then the total sound is going to be almost negligible due to the addition of this extra ancillary unit, additional noise making unit, right. So, this will be a very important formula as far as your selection of vendors for these ancillary units will be concerned. This is what you should demand. You should demand that the additional unit that is being procured from the vendor should have noise levels perceptibly lower, much lower, and how much lower you can look from this chart. If you cross this 10 dB limit, you are quite sure that this is not going to affect, right. Okay. So, if we know addition, subtraction should not be too difficult. The subtraction formula, I will just run through it quickly. So, now it is the other way around. Let us say in a shop floor kind of environment where there are many different machines, and it is very difficult to shut down all the machines and measure out the sound emanated by one particular machine, right. Suppose for some reason you are thinking that a particular machine is not working correctly, and you need to have to know, just like our human ear can possibly get accustomed to the sound of it, and if we hear a different sound when we ride our bicycle every morning, then we are almost sure that it needs certain overhauling and some oiling is required. So, similar things do happen in condition monitoring of machines also, but again in a factory environment you are not expected to switch off all the machines and take the measurement of one particular machine in isolation. You have to do it in a more efficient fashion. So, the way it is done is that you measure the total noise and then you shut down only one machine, the machine associated with the one that you are investigating, right. And using this subtraction formula, you can recover what is the noise emanated by this machine in isolation, right. So, that is how this formula will be applicable in the field. So, the total sound, which is abbreviated as L subscript T, is given as 10 log 10 the mean square of the total sound divided by the P reference square. So, that could be turned around and written as 10 to the power L T by 10 is this total sound, which is P T RMS square by P ref square, and we already know that the total RMS is P 1 RMS square and P2 RMS square, just simply add it. So, therefore, we know that 10 to the power LT by 10 is 10 to the power L1 by 10 plus 10 to the power L2 by 10. We just turn this around and write it in this following form, where 10 to the power L1 by T is L1 by 10 is 10 to the power LT by 10 minus 10 to the power L2 by 10, right. So, therefore, L1 can be written as, if you take logarithm of it and multiply by 10, you will get 10 log 10, 10 to the power LT by 10 minus 10 to the power L2 by 10. So, this is the formula by which, if you know the total sound and if you know the sound of the sound obtained with one machine switched off, you could actually recover the sound associated with the machine under investigation. That is typically the case which will be used in different shop floor kinds of environment. Also, another way in which this formula comes handy is with regards to noise source ranking. I think I will talk about noise source ranking in little more details in few slides down the line. So, I will refrain myself to talk about noise source ranking. So, here is another example using this sort of a chart. So, here we had a total noise of 60 dB, that is the background noise together with the machine noise is 60 dB. The background noise was measured as 53 dB. The difference, which is just the arithmetic difference, turns out therefore to be 7 dB. So, 7 dB in turn means, through this correction chart we get that we have to subtract just 1 dB. So, therefore, the noise of the machine under investigation is 59 dB. In other words, 59 dB plus 53 dB should give us 60 dB, right. 59 dB plus 63 dB added logarithmically is going to give us a total sound of 60 decibels. Okay. So, here we are about noise source ranking. As I said, the dB subtraction formula is very useful for the exercise of noise source ranking. Whenever you, as a NVH engineer, you have to the first job rather of an NVH engineer would possibly be to identify which is the most noisiest component of your product, right. This is very important, because what the dB addition and dB subtraction formula in fact tells you is that unless you target the noisiest component of your machine, you will not be able to make any substantial gain in the total noise. Suppose you have in your machine two components, and both of the components, let us say engine and the transmission, both of the components are noisemakers in isolation, but the point is, at the vehicle level, when both the components are working, you should be able to identify which is the most noisiest source. If it so happens that the noisiest source is the engine, and just to give you some example numbers, let us say the engine is at 90 dB and the transmission is at 84 dB, then it will actually not help much, I mean very marginal help gains or almost no perceptible gains in terms of the sound levels will be obtained if you concentrate your efforts to silence the transmission rather than the engine, right. Because just from this dB level itself you can understand that if that 84 dB, even if you reduce to 80 dB, nothing much will happen. If 90 plus 84 is adding up to something, then 90 plus 80 will add up to almost the same number, right. So, you will not be able to get any gains in as far as the total noise is concerned, unless you target the right source of sound. And there is that is why the importance of noise source ranking is very important for the life of an NVH engineer. So, usually for any machine, let us say something like a vehicle or even something like an air conditioning example, you will have lots of components which are potential noisemakers. You must have a well defined procedure by which you can rank these different sources of noise and then concentrate your analysis towards improving the noise characteristics of the noisiest source, rather than trying to dedicate your efforts to each and every component. You should attack right at the source of the noise, and only if you are able to mitigate the primary source will you achieve any substantial gains towards the total noise of your component. So, ranking in order of importance of different sources of noise in the product is extremely important, because unless you do so, you are not be able to translate or get any substantial gains as far as the total noise of the product is concerned. So, noise control treatment therefore has to be focused on the most noisy element, and you have to identify that in a particular process, which is what I would elaborate to you in a moment. So, there are different components, just like for the example that we are talking about, let us talk about a vehicle. So, in a vehicle, as you know, the engine is a noise source, the exhaust is a noise source, the intake is a noise source, the road noise is a matter of concern, transmission is a noise source, air condition is a noise source. So, the question is, how will you in a sort of feasible and economical fashion rank each of these source in terms of its importance. The idea is actually pretty simple. We have something called noise absorbers, which are like fibrous materials. So, if each of these noise sources are sort of covered with these absorbers, it is expected that the noise emanated from these machines will substantially reduce. But then you cannot sell a vehicle where your engine as well as the gearbox and everything gets cladded with these fibrous materials, because usually the longevity of this fibrous material is not very high. So, especially because of the temperature effects and the dust effects, they tend to get spoiled. The ones which are like more reliable and more durable are extremely costly. So, the process by which the noise from individual sources of the vehicle will be estimated is the following. So, first we take a measurement of the total vehicle noise, that is we call it as measurement 1, and second time we repeat the same experiment, but this time we clad the product of our interest, let us say the engine, with these absorbing materials as was discussed. So, this would be called as measurement 2. So, using the dB subtraction rule, we will subtract measurement 2 from measurement 1, and as a result what we will get is the noise produced by the engine. So, in this fashion we can estimate the noise due to each and every product within the vehicle. So, here is an example where we employ the dB subtraction rule as was explained in the previous slide. So, here in practical applications such as in vehicle, we know that there are lots of noise sources. So, typically in a vehicle you will find the engine, the transmission, the intake, the exhaust, the tires, all of them contributing to the total noise. As a vehicle manufacturer, one needs to have a clear idea that which of these components are important noise makers, and accordingly target those components rather than grappling in the dark and trying to at random trying to control the noise of any of these individual products. So, what is usually done is the following. A measurement of the total noise is taken, and that is what you see as the total vehicle noise, which is plotted in solid line along with circular dots. Then followed by that, for example, if you are interested to find out what is the engine noise in isolation, then the engine is sort of covered with noise absorbing materials and another reading is taken. This reading is subtracted from the first reading, then what you get to is the engine noise. So, the noise reading that was obtained when the engine was shrouded properly with a acoustic absorber, in that noise reading the effect of engine noise would possibly have been struck off, and as a result that measurement will include the measurement of all noise other than the engine, and then from the total vehicle noise, if you subtract that noise, the noise due to all other components excepting the engine, then you will land up with the noise from the engine in isolation. So, using this procedure of dB subtraction between these two measurements which I have just talked, you will be able to recover the engine noise in isolation. This exercise is very important from the application point of view. As I said, that the noise source ranking is an important exercise in industrial application, because only through noise source ranking in industrial applications can you really zoom in to the source of noise and then take appropriate corrective actions for the refinement of the noise. Coming back to the results shown in this slide, what you see here is not only the engine noise in isolation, but also the intake and the exhaust noise, and also the tire noise. So when you superpose all these noise readings that have been taken through the appropriate measurement procedure as discussed, and overlay these graphs together, then we get a very informative picture of the different components of noise that are being contributed by the different products within this assembly. For example, in the low frequency zone between 100 to 300, 400 possibly, what you see is that the exhaust noise, which is shown in dotted lines together with a marker which looks like an hourglass, and that is contributing to the total vehicle noise. So if you wish to get any reduction of the low frequency noise, then one has to target the exhaust, possibly design better mufflers. Similarly, the intake noise has a peak at a single frequency. You can observe a distinct peak in possibly the third vertical line. But again, on the high frequency side, it is the engine noise which dominantly latches on to the total vehicle noise. So in the high frequency side, if you want to get any benefits, then one has to look for major refinements in the engine structure and try to bring down the engine noise. If engine noise is brought down at the high frequencies region, then the total vehicle noise in the high frequency will also be controlled. But having said that, we must realize that the overall SPL is contributed by all these components, and the overall SPL across the frequency, or the overall dB level here, will be reduced if one can control the either the low frequency noise through the exhaust or the high frequency noise which is happening just around 1000 hertz. So looking at this chart as a acoustician, I would like to recommend that one has to take care that near about 1000 hertz the engine noise must be reduced, and near about 100 hertz the exhaust noise must be reduced. So we must design a muffler for this vehicle such that the performance at 100 hertz comes down. We must do something even at the intake noise such that the frequency corresponding to that third grid line, which is possibly like 500 hertz or so, should come down, and the engine structure must be redesigned such that the frequency peak again corresponding to 1000 hertz comes down. You will note that each of these frequencies are like the bounds of the total vehicle noise curve, and therefore if you want to bring down the total vehicle noise, these are the design changes that you must do to your vehicle so as to manifest considerable noise improvement in the noise performance. Okay, so I think we'll stop here, and we'll take it out from here in the next class.